So we know that squeeze theorem tells us that when we have two known functions, we'll say we have g of x, and then we know that g of x is less than but equal to some sort of other function, we'll say f of x, right? And we also know that f of x is less than but equal to another function. Let's say this one is h of x, right? These functions, right? These will either be given, or you'll need to find them. And I'll show you how to do both. So let's say when we're given, right? We know this function, we know g of x and we know h of x. And we're told to ask what the limit is as x approaches some sort of value. Let's say this value is c of the middle function of f of x, right? And it's unknown. We don't know. But we do know g of x and we know h of x. And let's say we have the limit as x approaches the same value. We're approaching the same thing for g of x. And we're told it equals some sort of value. Let's label this value as L. And we also know that the limit as x approaches c, as we're approaching the same thing, for h of x, it's also L, right? Some sort of value. So therefore, because these are equal, it only makes sense that the limit as x approaches c of f of x must also be equal to L, right? Because we have the limit as x approaches some sort of value for g of x is less than but equal to f of x, and f of x is less than but equal to the limit as x approaches some sort of value c of h of x, and we know this is L, then and L is less than but equal to f of x, then f of x is less than but equal to L. So therefore, to support this inequality, right, because we have less than but equal to make this inequality true, f of x, the limit of f of x, must also be equal to L. Any other value would not satisfy squeeze theorem, right? And squeeze theorem means what it says, right? Like let's take, for instance, we have a coordinate plane. Let's say our y-axis and our x-axis, right? And then we have some sort of function, right? Let's label this function as g of x. And we have another function. Let's say this is h of x, right? And you can kind of see how they're like squeezing in on a certain value. And we can know that they both approach the same value on this x-axis, or they both approach the same y value for their x value, right? And let's say we have an unknown function, right? And we have this function that just goes like this. We don't know what it is. Let's label this as f of x. By squeeze theorem, when we apply squeeze theorem, we know that if g of x is less than but equal to f of x, and we know that f of x is less than but equal to h of x, and we approach the same thing for g of x, and we approach the same thing for h of x, then to support that inequality, the limit as x approaches the same value must also be equal to f of x, right? And that's the idea. That's the premise of squeeze theorem. When we have two known functions, and we're kind of squeezing in on this unknown function to find the limit of the unknown function. So now that we know what squeeze theorem really tries to get to, let's work on some examples. Let's say we have a very similar function, like 8 minus x cubed is less than but equal to an unknown function, right? But then the unknown function f of x is less than but equal to 8 plus x cubed. And we're told to find the limit as x approaches 0 for f of x, right? In this case, we're given the functions, right? However, we're not given the middle function. We're not given what f of x is. But we can apply squeeze theorem to know what the value is for this limit. So if we apply the limit as x approaches 0 for 8 minus x cubed, and we do the limit to everything, right? The limit as x approaches f of x is also less than or equal to the limit as x approaches 0 of 8 plus x cubed, right? We can't exactly do this limit right now, but we can do the neighboring limits. So we do this limit, and we plug in, and we substitute 0 for x, the limit as x approaches 0, 8 minus 0 cubed. 8 minus 0 will just be 8. And we can bring this function down, and we know that this limit, we can't exactly solve it yet, right? 0 of f of x. But then we could do the right-sided limit too. If we substitute x for 0, right, we get 8 plus 0, which 8 plus 0 will just be 8, right? So therefore, to satisfy this inequality, regardless, right, if we know the function or not, the limit as x approaches 0 must be 8. It has to be 8 to satisfy this inequality. Because according to squeeze theorem, it tells us that. So therefore, we can conclude that the limit as x approaches 0 for f of x, although we don't know the function, must be equal to 0. Oh, sorry, must be equal to 8. All right, let's work on another example when we're not given the function values. Okay, let's work on this one. The limit as x approaches 0 for x squared sine of 1 over x. This problem does look a bit intimidating. But if we go back to our pre-calculus, what we learned in pre-calc, we know that sine, the function of sine, right? It is bound to the range of -1 and 1, right? It's bound to those values. So you can't have any value greater than 1, nor can you have any value less than -1, right? And we can look at this function and we could say, okay, well, what's the parent function, right? Because we know sine of x is bounded to this, but this may not be bounded to this exactly. But we're looking at where sine of x is. So we don't focus on this part, x squared, and we just focus solely on the sine and what's inside, right? We can apply its restrictions, or right, so then we have -1, and we apply the squeeze theorem. We know that -1 will have to be less than or equal to sine of -1x. And sine of -1x cannot be greater than, but it can be equal to 1, right? However, this isn't exactly what we're trying to find the limit of. So we multiply both or everything by x squared. So then now we have -x squared is less than but equal to x squared sine of 1 over x, and is less than but equal to x squared. There you go. That looks exactly like what we're trying to find. So now we need to apply the limit. So we do the limit to everything. So the limit as x approaches 0 for -x squared is going to be less than but equal to the limit as x approaches 0 of x squared sine of 1 over x is less than but equal to the limit as x approaches 0 of x squared. So then, although we don't know what this limit is, right? We don't know what this one is. We do, or we can find the limit of these functions and then apply the limit definition to find what this truly equals. So then we know that the limit as x approaches 0 of x squared is just 0. We can just substitute 0 into x squared. It will be 0, and at negative times 0 is just going to be 0. So we know that the limit as x approaches 0 for -x squared equals 0. And we go to the right, and we do the limit as x approaches 0. 0 squared is just 0. So there we go. We know that these functions are equal to each other. These functions, because they equal the same thing, right? We have 0 is less than or equal to the limit as x approaches 0 of x squared sine of 1 over x is less than but equal to 0. So to satisfy this inequality, what must the middle limit be equal to? It must be equal to 0. So this has to equal to 0. And that's how we solve a limit when we're not exactly given our function values, our g of x and our h of x, right? When we're not given these values, we have to find the restrictions of the middle function or the function value that we're given. However, if we're given the function values, we don't have to find the restrictions of the function, and we can just apply the limit to both sides and find what those limits equal, and then that must be equal to the unknown function.